This conference will now be recorded.
Okay.
Thank you, Ash. Thank you very much.
But by the way, we are still we still have to upload the recordings. We have all of them. I mean, we have not forgotten this every time. It's just we still need to upload them to the wiki page, but this will be done as soon as possible.
Yeah, honey, if you need any help, please let me know, because in Michael's absence, yours truly will be doing all of it.
Okay.
So I will be the one helping you with the YouTube links and whatever else you need. So
okay, great. Thank you very much.
We can take that offline. Yep.
I'll ping you then afterwards. Perfect. So welcome everybody to the heat reuse work stream, to the heat reuse call. Today we have a really small, short recap as always, who we are, what we do, where to find the important informations, and then we will have the presentation from Danfoss from here, our welcome Drew here. I make like this. Okay, perfect. And well, so just very direct to the topic. Here's our wiki page. Cosimo already put this link on the chat, so you can easily copy that and check all the information uploaded. We have a calendar of events, what we do every time. So besides these presentations, we discuss about the content of a white paper, of a kind of guideline we want to publish as an outcome of our work for I would say facilitating future developers for integrating heat reuse projects in their future data centers. So this is our mail address if you want to write us an email or some Christmas greetings, and well, and here Cosimo and me, Jaime, as colleagues of this work stream. So the objectives are to gather use cases of data center heat reuse, waste heat reuse. Some guys do not like this waste word. Some other actually use that. This can of course originate a discussion in the future codes if you want. But well, here I put waste heat reuse, suggest different technologies for capturing the waste heat and see different ways for doing that. Talk about challenges and opportunities, and talk about the metrics around heat reuse. And
ja, ik heb hem al zacht gezet.
Okay, there's somebody there.
I'll mute him.
Some background is right. Thanks, Cosimo. So as I said, as an outcome, we want to elaborate a guideline, a white paper, and of course make some noise and generate some change in the industry and make possible that heat reuse is being seen in as many projects as possible everywhere in the globe. So not only in Europe, but also in the US and of course in Asia Pacific. That's why we are also doing these calls every first Thursday of the month. So far, we have had a lot of presentations of use cases. Last time, Block Heating was here. This company from the Netherlands, putting some small data centers close to the fields, so to greenhouses in Netherlands, and offering cloud services or metal as a service, cloud services on that data centers, and utilizing the waste heat of those data centers for heating those greenhouses. We are actually trying to map all the use cases or all the fields where data centers heat reuse can be usable, and all applications in the industries where we can even have needs of heating energy at different temperature levels. And one of our latest actions is to quantify what do we need for 1 megawatt of data center connected to, for example, a pool, a huge swimming pool, which needs to be heated during the winter. And we are trying to use that example to quantify the capex investment, and also to define, to give it as an example for the sake of our guideline as well. And just to finish, before we give the word to our colleague from Danfoss, and the next presentations for use cases will be, which are actually also in our calendar. We will have somebody from Stanford University presenting their huge knowledge about heat recovery at data centers. This will be 31st of May, And the 26th of July, we have Carnot Computing, a French company, also doing heat reuse actually actively in their data centers, which are actually more or less edge data centers. In between, it's not that we're not going to have calls. We will have calls, of course, but we will discuss the content of the white paper, because this is also actually what we want to have as outcome, not only use cases, not only a bunch of use cases, but to discuss and put something into paper. And as Don just said, we have the tech talks. One tech talk where Cosimo will participate, actually wasn't mentioned, the 19th of May, and I will talk at the 24th of May in the OCP Tech Talks, where you're welcome, of course. Well, that's it. I hope you enjoyed another presentation from Drew.
Yeah, just two housekeeping comments. If you can put the company, your affiliation next to your name, that helps. And if you have questions, please use the chat box, and Jaime and I will handle the chat box and see if we can answer your questions. Unfortunately, today, both of us, we have a hard stop at the top of the hour. Normally, we actually linger a little longer, but today we have to go. So if you have questions that have not been addressed, Jaime and I just put our emails in the chat box. You can contact us at any time. That being said, and without any further ado, Drew, the floor is yours.
Thanks, Cosimo. Let me know when my screen comes up.
We can see it.
Okay.
You're good to go.
Yeah.
Excellent. You guys can hear me okay?
Yes.
Okay, excellent. All right, so my name is Drew Turner. Thanks everybody. Thanks to OCP for giving me this opportunity. Really appreciate it. Have a few Danfoss colleagues that are on the call with us as well. And what I'm going to be speaking to today, relative to the other heat reuse topics, is especially on our experience with designing systems for heat recovery and heat pump applications, and basically making the case on why critical facility cooling heat recovery is the best opportunity for base loading future heat supply, whether it's going to an industry or to a district scale application or neighboring building heat reuse. I'm going to be speaking to this based on experience over the last couple of years designing systems for these applications, and comparing and contrasting it to the other application experiences, and how that has led us to these critical facility cooling applications and heat recovery, and especially data centers, as the best opportunity for heat reuse, heat recovery and heat reuse, and base loading future heat supply. Just a little background on me. I've been with Danfoss for 8 years now. I'm based here in Pueblo, Colorado. So good morning to the US colleagues, and good afternoon to the European ones, and good evening to the Asian ones. But I've been in the industry now for 25 years. Started first 17 with Train prior to coming to Danfoss, which is why I'm located here in Pueblo. And I am the global head of Danfoss Sector Integration, which is a newer organization within Danfoss that is really focused on these sector integration opportunities. Jaime spoke to the term heat recovery or heat reuse, and people speaking to issues with that. And that's one of the things that we've expressed, is that the critical factor here is moving the industry to integrated systems design from a cooling and from a heating standpoint. And this is really all of the applications and experiences that I'm going to be speaking to are based on that, what has driven to that view, that it's not about heat reuse, because then you're really calling it a secondary byproduct that you're utilizing. And what we've been focused on is helping to drive the industry to integrated system designs from the beginning, such that it's not an afterthought on recovery and reuse. But it's important to give the context of the opportunity and the associated trends. And in the US, and this is the picture specifically for the US, the electrification of heating and heat pump integration is really driven by the decarbonization potential coming from the integration of renewables into the electrical grid. And what we've seen, on average, we're a little bit behind Europe overall, and especially behind the Scandinavian countries, where the experience that I'm going to be speaking to later is really a majority of those applications were done or have been worked on. But in the US, there is a significantly growing percentage of the electrical power that's coming from renewables. That in turn increases the potential for the decarbonization from the electrification of heating via heat recovery and heat pumps. And that's really the main driver for all of this. And what you see is today, or actually a couple of years ago, we were at about 21%. We first did this chart a couple of years before that, and it was about 19%. So it's growing about 1% per year right now, as far as electrical generation coming from renewables into the power grid, and it's accelerating. So that one is growing up to 1.1, et cetera, per year percent of power coming from it. But that's really driven, as you can see on the right-hand side, by the growth of solar integration into the renewables and to the power grid as well. Historic growth has really been driven by wind, but the future and what we're seeing now is it's really being driven by solar integration. And the reason for that, and this is another chart that's really changed over the last couple of years. It's a fantastic chart coming from ACEEE, but it talks about the power costs associated with the power production coming from different sources. And what's changed in the last couple of years is that renewables have shifted to the point where they're now the lowest cost energy source into the power grid. So next to energy efficiency, which is very much tied to what we're doing on heat recovery and heat pumps, in other words, with energy efficiency, of course, the power that you don't use is the cheapest source for somebody else in the power grid. But outside of energy efficiency, the renewables are now the lowest cost source. And a couple of years ago, this was not the case. And so the way we see it is this moves it beyond a political issue to where it's now, because it's the lowest cost source, you're going to see that acceleration growth because it's no longer a political issue. It's a financial, almost strictly a financial issue. And corresponding to this, as you integrate heat pumps into to drive the electrification of heating, as you grow the percent of renewables that are built into the power grid, the percentage or the CO2 emissions reduction coming from those heat pumps replacing the fossil fuel sources grows. So as you grow from no renewables to 10% to 20%, et cetera, you're increasing the business case, the decarbonization business case for the heat pumps that have been implemented. But there is the potential for it to become a political issue again, and this is what we're trying to help avoid by focusing on the larger scale heat recovery and lower cost heat recovery and heat pump applications. The risk and the potential risk that we see coming that has actually been realized to some extent in the countries that have significantly already electrified their power grid or their heating sources is that you're creating a disconnect by the integration of renewables into the power grid between supply and demand. So as you grow the percent of renewable or percent of power coming from renewables, you're creating that disconnect between supply and demand, driven by the fact that the wind only blows when it wants and the sun only shines when it wants. How you address that disconnect is, of course, in the form of energy storage. The larger scale you go in terms of the heat recovery and the more efficient that you go in terms of the heat reuse and the heat recovery heat pump systems, the more you can address that potential risk by creating a resilient demand side district or energy system, whether it's on the district scale or in the individual building scales. And those storage sources, of course, come in different forms. It comes in batteries. You generally see a transition in the industry to focusing on storage, short-term storage, i.e. thermal storage, medium-term storage in the form of batteries, and larger scale and longer term storage in the form of hydrogen, et cetera, and also for transportation. One of the other main points that we try to make is that everything is linked. When you look at the trends and the trend from climate change going down to the electrification of heating and renewables integration, everything is linked together. And anything that is not linked in terms of these trends and the flow, how we see the flow down happening, means that it is not going to present a significant opportunity and focus from a Danfoss and solution standpoint. But this is the way we see it. As you drive down the flow from the climate change itself to the renewables and electrification, sector coupling, integration of heating and cooling systems together, all of this points you to, and it's not intuitive when you look at this at first, but all of this points you to these large scale critical facility cooling systems as your best source for the future heat supply. And focusing on those from a solution standpoint is a critical strategy factor as we see it within Danfoss. Our experience, I'm going to speak to a lot of our experience designing systems over the last couple of years, but to give it context and to give it also the experience from actual cases that we have implemented at our Danfoss facilities, I'm going to speak to those experiences in Norborg, Denmark. And so what I show here is the heat produced or used by our Danfoss facility in Norborg and how that has decreased over the last several years. As you may be familiar, Danfoss has committed to be carbon neutral by 2030. And Norborg has committed to be carbon neutral by, I think we just reached it, but the goal was 2025. And this has actually been in the works for a number of years now. But more recently, it's become more of a challenge because you're just reducing energy usage via energy efficiency and implementing more efficient systems and reducing temperatures, et cetera. That was what we would call the low-hanging fruit. The more complicated is electrifying the tougher to electrify systems, including process heating, et cetera. But a lot of our experience over the last few years and what we see going forward is an integration of heat pumps into our facilities and to electrify those heating sources. One of those examples is on a data center, and this is our own data center there in Norborg. And actually, this is being implemented right now as we speak, and it is retrofitting a data center cooling system that we implemented a couple years ago. So what you see here is just the chart of the chillers, adiabatic cooled chillers, which were implemented to cool the data center at our own facility and providing cooling to the data center at 20 degrees Celsius. What we're retrofitting is it to a water-to-water heat pump system. And this water-to-water heat pump system is, of course, cooling. It's basically integrating into the existing cooling system on the cooling return line such that it becomes the base load or pre-cooling of that data center cooling system. Then the existing equipment at the facility becomes the existing cooling equipment that we installed a couple of years ago becomes a backup. This is, from our learning experience, a fantastic opportunity also externally. And we're working on several projects now to do similar things for external customers. But one of the main messages or points that we try to get across is this is a very simple retrofit, because all you're doing again is tying into the return line of the existing cooling system, assuming that it's a chilled water cooling system from first implementation standpoint. You're retrofitting that existing chilled water cooling system, tying into the return line to basically be the pre-cooling of that data center cooling system. And then utilizing that, of course, to recover heat to the district energy system. The only difference with this water-to-water heat pump versus, say, a water-cooled chiller is that you're controlling it based on the heating temperature and the associated capacity coming from that. So it preloads based on the heating temperature and capacity requirements on the demand side, district energy, but tying into that district energy system on the demand side, you're basically ensured that you're going to be utilizing that heat all of the time, such that those air-cooled chillers or adiabatic cooled chillers become a very rarely used backup. When we did this, we started looking at the modeling of what the performance should be. And when you look at the modeling, and one of the other points that we make is data centers, of course, are, and this is no news for anybody on this call, but it's a critical one when we're talking to customers about this. As you increase the cooling temperature of the data centers, you become more valuable to the heating customer because you have to do less work to get it to the useful heat temperature for the district heating system or whoever the customer is going to be. When you look at it from an individual compressor standpoint, the efficiency that you see down here below, David on the call is going to be very familiar with this. But your performance for the 20 degrees Celsius that we were cooling our data center at, the cooling performance from a design standpoint, if you just look at the individual compressor, is about 3.44. The heating performance is about 4.44 COP. The symbiosis, and that's our term for this, but the symbiosis efficiency or the combined cooling and heating efficiency is 7.88. That's the individual compressor. You'll notice up above that the data center performance of this water-to-water heat pump that we're implementing from a heating standpoint is significantly above the 4.44 that we showed down below. The reason for that is because of what you can do from a system design standpoint of the water-to-water heat pump system that you apply to it. And so that's both based on the compressor optimization as well as the heat pump circuiting and system optimization. But for this, and what we've done for a majority of the external opportunities that we worked on as well, is design a series counterflow system. That high differential that you're moving to with data centers and the cooling system, that higher differential, combined with the higher differential that's the normal practice, both for an individual building on the heating side, more in the 20K differential range versus cooling normally at around a 7 to 10K differential. That differential drives the opportunity to optimize the system with a series counterflow heat pump, water-to-water heat pump system that in turn increases the overall efficiency, in this case by around 18%. But again, the main takeaway is, of course, the increased cooling temperature increases the efficiency of the water-to-water heat pump because you have to do less work, about 2% per 1K differential that you have to do, or a reduction in 1K that you have to do. But it also comes from the compressor optimizations. So with compressors, and this is not only true for the compressors pictured here, but for other technologies as well. In general, you'll have optimized compressor designs to the differential that the application is doing. In the case of the compressors shown here, the turbocore compressors utilized on this application and the external ones that we're working on, most of the external ones we're working on as well, we utilize a combination of the medium and high lift optimized compressor designs. And that in turn drives the efficiency benefit that you get from the series counterflow arrangement of that water-to-water heat pump circuiting, which is shown here. So you have one circuit doing the low stage, matching the lowest cooling water temperatures with the lowest return water temperatures coming from the district heating side, and you see that high differential. And then the high stage matching with the incoming return water coming from the data center and supplying the highest the hot water temperature going to the district heating system. So you use a combination of the medium lift optimized compressors on the low stage doing the lower differential, and then the high lift optimized compressors doing the high lift or the higher lift associated with the high stage. So it's a two-circuit design which drives that efficiency benefit, also with the compressor optimizations. But the compressor optimizations are a combination of both the power electronics design as well as primarily the aerodynamic design of the compressor and the compression process. That in turn drives the efficiency benefit. So again, from a symbiosis efficiency standpoint, what we did is we compared this to the cooling efficiency of the cooling going to the data center at the original design with that adiabatic cooled chiller. So supplying the 20 degrees Celsius on the design day, it was about 5.7 COP. If you look at the water-to-water heat pump, that is just supplying heat to the district heating system. So if you're not benefiting from the cooling, you just look at the heating, then the efficiency is not as great, right? Because you're just looking at the capacity coming from the heating side. But if you combine that with the cooling that's supplied to the data center and take that overall kW that you get on both the cooling side and the heating side and divide it by the kW usage of the water-to-water heat pump, the efficiency, of course, goes up significantly. But that assumes that you have the dual revenue path, and I'll come back to that here in a minute. I've been going for a while now. Sorry. Any questions? Anything I can clarify?
I actually have a question, but I wonder if you talk about, do you have a return on investment on that retrofit?
Yeah, on the retrofit, on our own data center retrofit, of course, from a CapEx standpoint, that's Cosmo, right? It's a little bit, the game is a little bit changed, right? Because we're looking at it from a cost standpoint, because the majority of the components coming into this are Danfoss. But so we're artificially decreasing the payback, but it is definitely going to be less than 3 years when the data center is fully loaded. But it's not fully loaded today.
You said 3 years?
Less than 3 years.
Okay, thank you.
So actually, with the cost basis of the Danfoss components going into it, it should be less than 2 years with the fully loaded. But I'll come back to that.
Drew, one question is about transition from air cooling to new cooling solution. I mean, is there opportunity to use on the cooling side new temperatures, higher temperatures?
Absolutely. And that's a really good question, because we are actually planning to expand the data center. We've had the phase 1 implementation of our data center, and we have a phase 2 and phase 3. And when we do that, one of the things, based on the learnings of, as you increase the cooling temperature, you increase the overall efficiency of the heat provided in addition to the cooling provided to the data center itself. From that learning, we're increasing the cooling temperature, and we're looking at alternative solutions, including liquid cooling for the phase 2 and phase 3. Does that answer the question? But just to finish it off, from the liquid cooling standpoint, you're getting into the range of, I looked at a range of 15 to 25 degrees Celsius, but you're actually getting into a range of, depending on the liquid cooling technology that you use, whether it's submerged or direct on chip and the different solutions that you have, you can get into the range of 35 to 50 degrees C, as others on the call know well. So that in turn, of course, significantly decreases the work that the compressors have to do, to the point where we could theoretically, if we enable it with our low lift optimized compressor designs that were shown here, the ones that are shaded out here, those are the most efficient. From a cooling standpoint, those are going to be operating in an efficiency of 7 to 8 or even higher COP. But that low differential, you're doing less than 32K differential theoretically with a liquid cooling system. So if we enable that higher suction temperature as well as higher discharge temperature operation that we don't have today on these compressors, then theoretically we should be able to use those for that liquid cooling to also supply heat to the district heating. That's the opportunity that we see.
Right. Just a time check, 10 minutes.
Oh, okay. All right. Yeah, I need to hurry then. Okay. So a key question when you look at doing these retrofits is, of course, what's the business model? What are you working with? And what we've learned is that from working with the data center, especially your larger mega scale or enterprise scale data centers, rather than trying to bang your head against the wall and change the focus on PUE and the focus on cooling, providing cooling to data centers, it's better to work with the district energy utilities to enable this. In other words, for them to make the case to the data center to integrate in and provide free cooling to the data center, and then recover the heat to the district energy system, such that the utility or whoever is the user of the heat becomes the owner of those assets, again, providing free cooling to that data center, true free cooling to that data center. And this is Cosimo, to your question, this is the business case, if you will, but it doesn't include the cost side, just the benefit side on our own data center. But the design heat capacity on that data center is about 618 kW based on 500 kW on the cooling side. And the operating hours, of course, 24 hours a day, which is another reason, of course, we're focused on these critical facility cooling system retrofits, because you have a relatively constant load from the cooling side, which in turn means relatively constant heat on the heating side. And based on that, when it's fully loaded, this is the heat production. And the normalized value based on the heating price, and this is before the escalation later in last year on the heating price escalation that we saw, and I'm gonna come back to that here in a few minutes, was about 267 DKK per megawatt hour. And the normalized heat value from that is coming out at 350,000 euros or 315,000 euros per megawatt data center heat capacity. The heat cost, depending on the cooling temperatures, comes out to about 240,000 euros per megawatt at 20 degrees Celsius, or at about 15 degrees Celsius, about 272,000 euros per megawatt. And again, just to emphasize it, increasing the cooling temperatures increases the waste heat value. In other words, the more valuable you are to the heating customer. But it doesn't necessarily, as you move to those higher heating temperatures, and as you move to those liquid cooling solutions, you also increase, to use the term coming from the CEM training, the heat quality, right? Because you're increasing the heat recovery temperature without boosting it, potentially without boosting it, to the point, and of course we've seen this in case Trenton joined us, a case for this up in Wyoming, where they're actually using the direct heat coming from the data center to the indoor grow houses. So depending on the customer and their heat demand, district heating, generally you're gonna have to boost it up to 65 to 75 to 80 degrees Celsius. But for indoor agriculture, where you're heating the food, that is the air coming into these plants to get them to the optimal growing temperature, most frequently, and especially as you increase that cooling temperature, you're not going to have to boost that heating. That in turn means a much lower CapEx solution to recover the heat, to the point where you don't need the water-to-water heat pump. Instead, you just need a heat exchanger, right, Cosimo, or heat exchanger and a heat transfer station to recover that heat to, for example, that indoor agriculture facility or that recirculated aquaculture system, where again, you're just maintaining a optimal growing temperature. Related to this, and another reason that we're focused on these critical facility cooling systems. So critical facility cooling systems we're focusing on because of the high cooling temperature, as opposed to comfort cooling, where you're cooling somebody at around and dehumidifying air at around 7 degrees Celsius. These critical facility cooling systems are operating at 15 to 20 to 25 and higher in the case of data centers cooling temperatures. But that constant heat that you get is one of the main reasons that we're focusing on it, or the second reason. The third reason is because of the backup power system itself. So if you're going to move to a base load heat recovery heat pump system for a district energy utility, you have to be the lowest cost source. District energy utilities operate basically the same as electric utilities, and having a base load, a middle load, and a peak load source based on the operating cost, startup cost, and operating cost. And so it becomes very critical to be the lowest cost source. And as you increase that cooling temperature, you're going to get to that point. But you're also creating the opportunity to recover the heat from that backup power system itself. And what we see is those backup power systems moving to more renewable sources in the future, such as hydrogen production, the hydrogen production and the hydrogen usage via the fuel cell, which are not extremely efficient processes, but all of that inefficiency is additional heat. So as you recover that heat, and also that electrolysis process degrades on performance over time, but that just means that it increases the potential for heat recovery. So as you make that transition, and as you potentially make the transition for that backup power system to become the primary energy source for the data center, utilizing the electrical grid instead as the backup, then you create that constant business case, if you will, for the heat recovery based on the production and usage of that hydrogen. We're also demonstrating this at our Danfoss Norberg facility. Related to this from an application standpoint is biogas facilities. Cosimo, I'm going to skip through this just in the interest of time. We are also working on a lot of hybrid opportunities. All of these are critical facility cooling systems that we're working on. That's why I'm highlighting them, but they're only related in that aspect. Of course, it's not tied to a data center. But this is at an actual district heat and energy utility itself, where we're taking the biomass, the exhaust coming from the boiler of that biomass system, cooling the scrubber water that's going into that exhaust gas to scrub out all the contaminants coming out of the exhaust, and then recovering the heat to the district energy system itself. And this is significantly boosting the efficiency of the overall heat provided. In turn, of course, justifying it being the base load system. And I'm gonna skip through this one. This is tying a cooling and heating system again together for a large warehouse, only related in that it's a critical facility cooling system. But it provided a very good business case to replace all the existing rooftop units, providing the HVAC cooling for this warehouse, and recovering the heat, recovering the heat from the refrigeration system and retrofitted that to a glycol cooling system. And this is another case where we're preheating boiler water, going into a boiler that is in turn heating an industrial process, another critical facility, and replacing a steam-fired absorption chiller, which was using that low-pressure steam coming out of that boiler to cool that same manufacturing process, replacing it with a water-to-water heat pump, which in turn, because of the higher heating temperature, which is preheating that boiler feed water, that higher heating temperature and the remaining heat that you have to reject, you don't have to use the cooling tower fans anymore to do it, and providing a very attractive business case. This is our overall experience. So just to summarize, over the last 3 years or 2 to 3 years, we've been working on these heat recovery heat pump applications, including on data centers, which you see here. Overall 8%, actually about 10% now of our experience. But critical facility cooling systems, you'll see as the biggest opportunities that we focused on. And there's a number of reasons for that, but the relatively constant load and the high cooling water temperatures shown down below in terms of a box plot with the average and then the range is a primary driver. And those data center cooling systems, of course, are increasing the cooling temperature and becoming a more efficient baseload source as you transition more to those higher temperature cooling technologies. And this is why it's critical, and I'm basically going to stop here. When you look at, and this is why with our presentation, we focus not just on the data center and heat reuse, but on the heat pump and comparing it to the other applications. One of the primary things that we see happening with the heat pumps and electrification of heating is utilizing air-to-water heat pumps. Air-to-water heat pumps are necessary because if you're going to electrify heating, there's only so much heat recovery that you can get. But they're a very poor baseload heat source, whether it's a district energy facility or an individual building. It's a very poor baseload heat source because of that operating cost based on the efficiency of that air-to-water heat pump. So in the case of the district energy utility where we applied our first water-to-water heat pumps, they also had a very large 7 megawatt air-to-water heat pump there, which was operating at about 3 to 3.5 COP. That was planned to be a baseload heat source for the district energy utility. Our flue gas scrubber cooling system that I showed earlier was operating at about 6 to 7 and in some cases higher COP. That in turn, when we saw the price escalation, meant that it became, along with the biomass system and the biomass boiler, the baseload heat source, continued to be the baseload heat source. But that air-to-water heat pump, which was planned to be based on expansion, that also a baseload heat source, has actually operated last year, as of October last year, only 300 hours the whole year. in effect becoming a peaking plant and not at the time that you really need a peaking plant. So this efficiency becomes very critical. And the reason it becomes critical is because of that same renewables growth that I spoke to earlier at the beginning of the presentation. As you increase the percentage of renewables into the power grid, if you don't build in significant storage to address that supply-demand disconnect, the way you see the impact of that and it potentially becoming a political issue again on the electrification of heating is in the form of that real-time electricity cost. And there's a very high variation in that real-time electricity cost. So renewables are about 50% of the power grid in Denmark today, as opposed to about 22% in the US. And they're seeing extremely high variation in real-time pricing on electricity, up to, in this case, October 21st of last year, roughly $120 per megawatt hour to $360 per megawatt hour, or 100 euros per megawatt hour to roughly 300 euros per megawatt hour in one day. And actually higher. We've seen it as much as 10 times higher than that in some cases. So this efficiency of the baseload heating system and recovering heat from a data center, and especially with the increase in cooling temperature, becomes very critical to that future baseload heat source if you're going to decarbonize the grid and do it in a cost-effective way, such that you don't have to increase the heat price and cost. So summary of the learnings, ambient air and water-based district heating heat pump systems should be from our perspective, should be the third priority. You know, they're critical, you have to do them because you can only get so much heat recovery, but the base load and the first focus for centralized heat generation for a district energy utility should be your data centers, basically, because of that efficiency, because of that higher cooling temperature, and because of that relatively constant capacity availability. And geothermal and comfort cooling applications fit somewhere in the middle as far as heat recovery. And of course, we have a broad portfolio of solutions for these. And this is what we've been working on, is designing these systems. So did I do it? Did I fit in the time?
You certainly did. You certainly did. Thank you very much. And there are a few questions, and you can probably see the chat yourself, but I can start, and then so like Herb is asking, wouldn't it be more efficient for district heating customers to disconnect and install the heat pumps in the buildings?
It's a good question. And if you use what I was just talking about on the air-to-water heat pump, the answer is definitely not, right? Because of that same factor, because of that efficiency of the air-to-water heat pump. You're generally going to be, that was a very efficient air-to-water heat pump, that 7 megawatt one that they did at that district heating utility. Again, they planned for that to be a base load. And so they used an ammonia system, which ammonia has a very efficient refrigeration cycle and is screw-based. It was a very efficient system, but it's still only 3 to 3.5 COP on that design day, on those cold days when it becomes most critical. As opposed to that, with a water-to-water heat pump in district energy, you're going to get 2, or in some cases even 3 times, based on our experience, the efficiency of that air-to-water heat pump on that individual building. So definitely much lower cost if you equate that district energy supply and the heat cost that they produce it at and sell it at to their customers, which in the case of Denmark, they're non-profits. So it's basically outside of the charges that they add in to develop additional heat sources. It's basically at cost, but it is going to be significantly lower cost than operating that air-to-water heat pump on that individual facility.
Actually, Drew, because people will tend to actually leave the call toward the end. If you can put your email in the chat, so if people want to contact you directly, that would be probably helpful.
Excellent, will do.
And the next question from Jaime. Maybe Jaime, you want to?
Yeah, I just take it over. I had 2 of them, so I just ask them at the same time. So how you talk about a use case in the Denmark, right? So the question is, if you envision other use cases in the US, somewhere else, you have many use cases in Europe, and how do you face these differences between lands? And the second question, totally different, is about storage tanks, because you showed storage tanks a lot of times, and I'm curious, is it's a standard for you, like you always have storage tanks and you do that yourself?
Really good questions. Okay, so answering the first one, US focus. We're focusing on basically where you can use large scale heat, right? And that includes especially cities such as New York City. I just left a call on what we're working on in New York City before this one. And campuses. Campuses are a fantastic opportunity because campuses, whether they're university campuses or large corporate campuses, you have the district scale of those, whether or not they actually have a district energy system today. They're working on those in the future. And the main trend that we see in campuses in the US is they have had district energy systems in the past, and they're going through the process right now that Europe and Denmark and others went through 20 years ago to transition from steam-based to hot water-based systems. So we're working with them on the various phases of that transition, including going from steam to hot water itself, and then hot water to lower temperature hot water via demand side changes, such as changing out radiators to fan coils and fan coils to underfloor. But facilitating that transition with the ultimate goal to implement the large scale heat recovery heat pumps, such as a geothermal based system or a data center or a university lab or any other critical facility that has backup. Hospital as that base load source.
Yeah.
And then, I'm sorry, what was the second question?
The storage tanks.
Yeah, storage tanks. Very good question because of the scale, right? This is another reason we're focused on district applications or large scale applications. The smaller you go, the more storage you have to build in because of that, for an integrated system, because of that cooling and heating disconnect. The larger scale you go in general, the less you have to address that disconnect. So you have that built-in storage or the thermal flywheel of the district energy system itself. So you have built-in storage, but the district scale also allows you to integrate different forms of storage. And we've worked on, storage systems to help address that disconnect at the district scale. But the main point is at the district scale, there's much less of a disconnect to address, right? Because you can pretty much constantly utilize whatever heat you can recover and use it as the base load.
Yeah.
I have a comment on that actually, to build on what actually Jaime asked and you just said, and you hinted that during the presentation that it should be the interest of the heat reuser, let's say the heat host, to present the data center the opportunity, right? Instead of the data center proactively reaching out for that. So one challenge that our heat reuse group has been working on with the different participants is that those are two very different words. So the data center and the heat reuse, normally they are very different companies. And then, as you said, in between, normally you have a utility company. And I would actually add a fourth layer, which is legislation. So you have some sort of legislative body in between as well. What has been your experience in combining all these different stakeholders?
That is the biggest issue that we faced with these. With focusing on an individual facility, the benefit is that you only have to have roughly 2 people nodding their head. If you're going to go on the district scale, you've got 10 plus people, and even more in the case of Denmark in some cases, that have to be all nodding their head at the same time. And
I'm nodding my head.
Yeah, the political factor, we like to think of ourselves, I think, as, technical and visionary experts in designing these systems, but that's useless unless you are able to, you're empathetic to the political factors that go into these decisions, and you know what the stakeholders are looking for. And especially when you're looking at 2 different primary stakeholders, the data center and the district utility, and then all of the stakeholders around them and the political folks that you mentioned, which are going to come into play on these when you're crossing property lines.
Yes.
You know, you always have to be able to speak in their language, which is no small task. And I'm still learning that.
Yeah, and I think you nailed that with there was a slide in your presentation where you just highlighted utility. And by the way, I think you turned off your camera, Drew. I don't know if.
Oh, did I? Sorry.
Yeah,
And,
you did.
so is where you just pointed out utility, right? So that you are going to actually address utility for that. So this is actually perfect.
Exactly. You know, you've got to start with for the critical facility cooling system retrofits, we figured out that the best business model is to start with the cooling customer and then to facilitate it with the district energy utility. We originally started going to the district energy utility, but we
Or
figured out
campuses.
that would,
Or campuses, as you mentioned, because in some cases you have all the stakeholders in the same organization. If you have a campus, it could be a university, as you said. It could be a large company. It could be a large hospital. So they could have a data center, campus with buildings, other facilities. So, but it is a challenge. And but before we actually reach the top of the hour, the last question that Jaime has actually
Okay.
there are two more questions, and we want to address both of them.
You just mentioned in one slide 20, I think it was, that you were using actually absorption cooling in one of your processes, which is actually very interesting. Was for a different thing, was not for a data center. But this is actually heat to cooling energy, and it's something actually we're envisioning for data center heat reuse. How do you see that? Do you use also absorption cooling? What are your thoughts about this?
in that case, we were replacing a steam-fired absorption chiller with a water-to-water heat pump, and recovering the heat to to preheat the feed water going into the boiler system. That was in turn then going back to that industrial process. Absorption cooling is, I have some background in that. It's kind of like, condensing boilers. You've got to have, in the future, you're going to have some level of condensing boilers. You're going to have some level of absorption chillers, and you're also going to have some level of organic Rankine cycle power production, right, for that heat reuse. All of those are opportunities, and they're all legitimate opportunities. Basically, it's whatever is the best opportunity based on the specifics of the application that you're targeting.
Yeah, one size fits all. It doesn't work in this.
Exactly.
Yeah, and the last question: is there reliability data for those types of compressors in this type of application? So any reliability concern? And put it this way.
I was trying to avoid giving a TurboCore marketing presentation, but if they're going to set me up with a question to do it, I mean, our experience with TurboCore and heat pumps is the exact same as our experience with TurboCore and oil-free, magnetic bearing-based technology in cooling applications as well. The great thing that you avoid with our technology for the heating applications is the issues that you run into with oil and the quality of oil and the oil management in those higher temperature applications, the breakdown of it. And so that in turn is going to drive if we can enable the technology to get to those temperatures. We have some limitations today, but we're working on expanding it. Those same issues, those same reliability and maintenance issues that you experience with oil management in other applications with those other alternative technologies become more critical for those heat pump applications because of the other factors that come into play when you get up into those higher temperatures.
Appreciate your response, Drew. Do you have actual data from your compressors in these applications that you can share? And I'm happy to drop my contact info in for an offline discussion.
I'm a Six Sigma guy, so we don't have enough data to give you really good data on it yet, but we're getting there, Matt. Yeah, I'll share with you if you want to drop it in there and share with you our experience so far.
That'd be great. Thanks, appreciate it.
Absolutely.
Okay, we actually reached the top of the hour. Drew, was a terrific presentation, a lot of data. Could you send us the PDF of that presentation so we can add it to the library?
Absolutely.
And if you have time to join our group in the other heat reuse calls, I'm sure you can add a lot of value.
Hey, Cosmo, can you hand over the screen to me?
Just did it.
I know you got to drop off, but I got a couple things I can say for people who want to stay on, if that makes sense.
Thank you, guys. I really have to go.
Cool. Hopefully I have control. I got it? Okay, hold on a second here. So I know that Cosmo and Jaime, I think you said you had to leave. Am I sharing anything right now?
Not really. Now.
How about now?
Now it's hit.
Okay. See if we can go through here a little bit and move some things around. This is not. All righty. What I'd like to do real quick is, and people can keep talking, but before we disappear, I want to highlight a couple things that are coming up that I didn't highlight earlier. One is 7x24. If you're going to 7x24, OCP is actually going to be presenting a discussion on COVID plus climate crisis equals better data centers. And the speakers on that, we're basically a case study of the Wyoming hyperscale white box story, which is a heat reuse project. It's going to be taking the waste heat. We'll be discussing that. Speakers of that, all these are members of participants of OCP, Trenton Thornock, Sam Allen, John Gross, and myself. This will be coming up at the 7x24 on the 15th of June. Want to kind of summarize what we said before, that the tech talks are coming up, and I gave a quick shot here of the agendas, 24th and 25th. It's kind of a summary of what all the cooling environments projects have been working on for the past 6 months, if you will, since we had Global Summit. And then the final thing here, I don't know if I really, but there's a talk at 4 o'clock Singapore time, which is roughly 1 o'clock a.m. my time, and we'll be having a Asia Pacific summary of what we've been covering. Does anybody else want to talk right now, or any comments? I know that it's after the hour, but if you're going to take advantage of this time and see if we can fill it with a little bit more. All right. Well, thank you very much. And as soon as I figure out how to do the controls, I will shut off the recording. Andres, you got a moment? You still there? I don't hear you.
Yes, I'm still here. I have a couple of minutes. Yes.
Okay, so what I started to show here, and I don't know if you can see it, is I may not be sharing it. Am I still sharing the screen or not?
Yes, you're still sharing.
Okay, so the topic, we're going to have cooling environment project update, and I'm going to run through this screen here with the people on the call. I'm looking for inputs from all the different sub-projects, and I'm going to do maybe a quick highlights of what they're working on, or I'll just run straight from this. Did you have something that, can you present a summary of what the heat reuse sub-project has been accomplishing since last April, our last call? Does that make sense? Maybe give it 5-minute summary?
I can give a 5-minute summary, yes. I was about to write you an email to discuss with you the agenda for Thursday. So it's fine.
Right. So what I'd like to give heat reuse like a 15-minute window to highlight. We don't have enough time in 1 hour to do anything really productive. So a lot of what we're really doing here is just highlighting what cooling environments is doing and inviting people to participate by seeing recordings or attending some of these other sessions. Mm-hmm. Does that make sense?
Yes. Yes, it does make sense.
So I was going to give you like a 10 or 15-minute window to give an heat reuse project update. And if Jaime wanted to do that, I mean, it doesn't have to be you, but someone from the heat reuse program just kind of highlight where we're going, what we've covered, and where we're going. Okay?
Yes. Yes,
That
I will
makes sense.
prepare
Is there
this.
anything else you want to talk about?
Sorry, I didn't got this.
Is there anything else you wanted to talk about at the
Yes, I would like to highlight the call for papers for the Future Technology Symposium. So
okay?
there's still 2 months left to submit. So I'd like to highlight this. And in addition, I would like to ask the Asia Pacific attendees what they wish to be discussed in this round there. So to include them more into the Asia Pacific call.
I appreciate that. We'll see how we get on attendance. I always try to find out what they want to hear, and for some reason, we've never had enough traction at the with the Asia Pacific call to get a quorum on what people want to hear. It's kind of one of those, we don't know what they want to hear, and the people that show up may not be the best indicators of what others want to hear. The ones who didn't show up are the ones we're trying to get on board. However, that
Yes,
having been
yes.
said, often there are several, Serene Au and Sabrina from, there are two ladies from, one's from Digital and one's from Microsoft, that are very influential people, and it's good to have them attend. So we do get some good attendees. Hopefully we'll get some more with this time slot. We'll see how it goes. But yes, I appreciate that.
Yeah,
Anything
okay.
else?
No, not related to the agenda. I have just a question to you. Have you already sent an invitation link? So I have none in my inbox. So maybe I just missed it, or it hasn't been sent
Maybe,
out.
hold on. I did send an invitation link,
Okay.
and that's something I do want. Let me. Here we go. I'm gonna add. Now, one thing. Let's see if this goes through. Did you get an invite? You should get an invite shortly if you haven't gotten it yet.
Okay. I will check. It hasn't arrived yet.
And all of a sudden, I realized I don't know that I've.
Ah, okay. No,
Have
no, it has arrived. Okay. Right. Okay. Now I have the invitation. Thank you.
I think we're still being recorded because I can't figure out how to turn off the recording. So it'll be interesting. Hopefully, I have to make sure that I have the ability to launch this. Let me try right now. I'm gonna anyway, I'll go close that. Did you get an invite from me yet?
I have received the invitation. Yes. So everything is fine now.
Or you did?
I did. Yes.
You did? Okay.
I have received the invitation.
Anything else you want to talk about now?
Sorry?
Is there anything else you want to talk about now?
There is only one point. Shall I start the meeting on Thursday, or would you like to do this? I can do this. Jaime gave me the
Sure,
credentials.
because you posted something on LinkedIn, correct?
I have posted something on LinkedIn, yes.
And I need to make sure that we're dealing with the same address. We'll do that right now.
it's always the same invitation link. So I have used this one here that we use here.
Oh, it's the same. It ends in 8085.
8085. Yes, yes, it's the same.
Okay. Then I will be forwarding your link on. So let me turn this back on just so that. So you can see, I think you can see,
Yes.
there's a fair number of people that I send invites to, and they always say if you want to be delete, please advise if you object to invites. A lot of people reject, but invites have gone out to a lot of people, so we'll see how it goes. Okay.
That's great. That's great.
Hey, I really appreciate all that Cloud and Heat's doing and all that you're doing, and having a lot of fun with it. Hope you're having fun too.
Yes,
Okay?
I do have. Yeah, thank you. Thank you. Thanks for your support.
Thanks.
Okay.
I'll let you go. Bye.
Okay, thank you. Bye bye.